Hello students and welcome to the lesson on complex numbers. And let's begin right away with our definition of an imaginary number. And the idea of an imaginary number came about when mathematicians were doing math and they came up with this problem. What is the square root of -1? Well, when we think about this, what are two numbers that when multiplied together would give you -1? Well, it turns out that any number, any two numbers multiplied together like this, multiplied by itself, would always give you a positive number. So you just keep in mind that if you have x squared, it's this answer right here, whatever this number here, will always be a positive number. Okay, so it's always going to be a positive number, which means it can't ever be equal to -1. But this situation does arise in math quite frequently, especially when we're working with quadratics. So mathematicians needed a way to write these numbers, and so they created a new set of numbers called imaginary numbers, and they defined the first imaginary number, I, as the square root of 1. And so let's see what that means. Well, it means that if you have I squared, that's I times I, or the square root of -1 times the square root of -1, which just equals to -1. So I squared equals -1. What about I to the third? Well, I to the third is really just I times I squared, which is I times -1, and that's -I. And then how about I to the fourth? Well, I to the fourth is really just I to the third, or I'm sorry, I times I to the third. And we know that I to the third is -I. We know that I to the third from the previous problem is -I. And so this gives you -I squared. But wait a minute, negative, so this is negative, right? But I squared from the previous problem is just -1. So now we're back to +1. So I'm going to write a short summary of all of this without all of the work here, just so that we can see. So we know that I is equal to the square root of -1. I squared is equal to -1. I to the third is -I. And I to the fourth is +1 again. And it's a little bit unusual when we're talking about imaginary numbers, but you'll see soon enough in this course that they really do have a use and many times a meaning to them. Okay? And I encourage you to work on this some more and try to answer these questions for yourself. What would I to the fifth be equal to? Or how about I to the sixth? What would that be equal to? So try to work on that on your own, and then ask your teacher if you have any questions on that, and you'll see that it leads to some surprising results. So now we have a definition of a complex number, and a complex number is a combination of a real and an imaginary number. So it's any number that can be written in this form, a plus bi. Okay, so it can be written as a plus bi, where a and b are real numbers. So a and b can be anything as long as they're real numbers. It can be integers, rational, irrationals, but you basically have a real component, a, and then a imaginary component, bi. So the complex numbers capture basically all the possible numbers that we have. As far as we're concerned at this point, it captures both the imaginary and the real numbers, okay? And just, as a side note, every real number can be written this way, okay? So we can say that every real number can be written as a complex number. So if you have a number like 3, okay, we can really just say that's just 3 plus 0i. Okay. And analogously, I'm not sure if that's a word, but every imaginary number can also be written as a complex number. So I can say that every imaginary number can also be written as a complex number. So if you have a number like 4i, well, that can just be written as 0 plus 4i. Okay, so complex number is just a way for us to write both, to combine together real and complex numbers. And again, this may seem a little bit weird right now, but there is a point where we will see that this becomes useful and it helps us to solve some of the problems and prove some of the theorems in mathematics. So let's see what happens in this first example when we start doing some arithmetic with complex numbers and seeing how they behave. Now, the rules for adding complex numbers are a little bit different than adding just purely real numbers. So for adding complex numbers, we simply add the real components. So in this case, that's 3 and 4. So we just do 3 plus 4, put those together, and then add the imaginary components. And that's 2i and negative 5i. So it's 2i minus 5i. And we put them together. Just like that. Simplify, and we get an answer of 7 plus a negative 3i, or just minus 3i. And there you have it. That is our answer. So the main thing here is just when we're dealing with arithmetic of complex numbers, at least when adding is concerned, we add the two real components and then we add the two imaginary components. And let's see what happens when we subtract. Well, the nice thing about adding and subtracting is they really behave similarly. So I'm just right here same rules as adding, just with a different sign. So we take the real components, 3 and 6, so you have 3 minus 6, and then we take the imaginary components, 2i and negative 5i, so this is 2i minus negative 5i, and then just simplify from there. So this will give us negative 3 and 2i minus negative 5i, which is really adding, and we get plus 7i. So adding and subtracting are very similar. They play by the same rules, and if you can see there's almost a symmetry between examples 1 and 2 because we're using the same values here when we're adding and subtracting. Or we're using similar values here when we're adding and subtracting. Alright, so we move on to multiplication of complex numbers. Now the rules here are a little bit different. It's not as simple as just multiplying the two complex and the two real parts. So we have to multiply each of the parts of the first number by every part of the second number. And so this is basically distributing. Or you may have heard of this described as FOIL. Okay, I don't like to use FOIL too frequently because there's some cases where it doesn't work, but the general idea is distributing. So we have to go 4 times 3, that gives me 12, and then 4 times negative 8i, which will give me negative 32i. Okay. Then I can do 7i times 3, which will give me 21i, and then 7i times negative 8i, which will give me negative 56i squared. Okay, so that was just foiling, similar to how we would do it when we have an algebra 1 or an algebra 2 type of problem. And so now we just need to simplify all of our terms. 12 is still 12. Negative 32i and 21i gives me negative 11i. And the nice thing about this last term here is that negative 56i squared, just remember that I squared is equal to negative 1. So negative 56i squared is really negative 56 times negative 1, which then gives you positive 56. And then when you combine the constants in the front here, in the front and the back here, we get 68 minus 11i. And that is your final answer. And when you multiply two complex numbers like this, you should end up with another complex number with some. You should not have I squared or I to the third or anything like that when you're multiplying just two complex numbers like this, because again the I squared terms is really just negative 1, and that will be converted back into a real number.